I audible? Yep. OK, cool. Thank you for the introduction. Hi, everyone. Thank you for joining the talk. Hope I can keep you all engaged enough for the next 60 minutes. I am a machine learning manager at Netflix, leading the foundation models team. Here the talk will cover some use cases from Netflix. But first and foremost, I wanted to have this slide where hopefully by the end of the talk, I will be able to convince you that in ML, there is a Harry Potter, and the Harry Potter has some magic wand to do something magical. Let's see if I manage to do that. But before, search and recommendation is kind of the overarching topic of this talk. And as we all know, like search and recommendations as application of machine learning is omnipresent in different products, whether it's video streaming service like Netflix or Hulu or Amazon, or music streaming service such as Spotify, Pandora, e-commerce platforms such as Etsy, Amazon, leverages ML, machine learning and AI for search and recommendations use cases. And the user base as well as the catalog is ever growing. So typically in industry, for solving search and recommendation tasks, by the way, how many folks are aware of search and recommendation and applications of ML? OK. I'm actually glad to see not that many hands, because I have a few introduction slides. But yeah, sorry for folks for whom it will be a little repetitive. So usually, because of the catalog is really big, in reality, for B2C, business to customer products, we have, let's say if it's a big company like Netflix or Spotify, there are 100 million plus users. Netflix has 300 million plus users. And the catalog, the items over which we have to score to show it to a user is usually more than 100 million. For example, in e-commerce context, probably it's in billions. So it's a very tough task for each of the user, rank the whole catalog and show it in front of you. And imagine when you join Netflix, you open your Netflix TV, and if it takes 5 minutes before anything shows up on the screen, it'll be ridiculous. So what do we typically do? Because the problem space to score is really high, is we usually break it down into 2 stages. So a user comes to, let's say, Netflix or Spotify or Amazon. There are millions of listings. There is usually a first stage, which is typically referred to as candidate set selection or retrieval, which reduces the number of candidates in the catalog to some hundreds of thousands of items. That then, a more complex model, usually referred to as second pass ranker, is used to then rank them for precision so that as a user, you see something that is personalized and useful to you and not the entire catalog. And this is a very usual 2-stage ranking in any industry setup for search and recommendation tasks. Today during my talk, I will focus more on the second pass ranker and then kind of generalize it to more foundation models. Usually, these are some common components for ML for product, ML or AI for product in the context of search and recommendation. As I mentioned, there is a first pass ranking, which could be a very simple, lightweight ML model or heuristic. And that's about the last time you'll hear about first pass ranking in this talk. And then we have second pass ranking, offline evaluation, inference setup, and A/B test, and online evaluation before it becomes available to 100% of the users. So second pass ranking has different stages that needs to be handled. First and foremost, where is the data? How do we get the data? What are the features? What is the model architecture? What is the objective? Should we optimize for click versus purchase versus keeping you engaged for more time versus just showing you something delightful for a few seconds? So it's really trying, objective and reward is somewhere where we really try to capture the business need and the user need. But before we can launch anything in front of real users, there's usually a very rigorous setup of offline evaluation to understand whether the model is doing what it's supposed to do before we show it to the user. So those are offline evaluations are kind of guardrails. And then once a model is ready to be shown to a user, there's a lot of inference considerations, like latency. As I was saying, if a user has to wait for 5 minutes to see a result, that probably will be a very horrible experience. So how do we optimize for latency? Some of you who work in ML infra space, you know, like P50, P90, what is the time end-to-end time that the model takes to return results. Throughput, compute cost, of course, now with GPU and stuff like that, cost is a big consideration. And finally, what are some user metrics that we leverage to assess whether this new model that we showed in front of all the users is relevant or not, and that's where A/B test metrics, score metrics, and so on comes in. So this is just an overview of different components. I would not go into details of each of these, but just wanted to share them here. In my talk, primarily I will focus on these 3 components. I think these are something I already covered, like second-pass ranker, offline evaluation, and inference. In inference, latency, throughput, and compute cost is very important. All right, now let me share a specific use case, a ranking use case, where in Netflix context, we proposed one model to serve both search and recommendation use case. Just a historical context, academically, search and recommendation has been approached in 2 different communities. There are conferences like Rexis that tackles recommendation tasks, and conferences like Sigaya tackles search tasks. But we basically said that, hey, you know what, this is ultimately, given the right context, it's kind of the same task, which is ranking. So the question we asked was, let me go to the next slide. Can we build a single model for both search and recommendation tasks? And the answer is yes. And just to kind of repeat the example of what is a search task, in the context of Netflix, when you type, let's say, PARI, which is a text, then we would expect the Netflix to return titles like Emily in Paris, or Cooking with Paris, like the actress Paris, and so on. Has anyone seen Emily in Paris here? OK, I really like the show. And then a pure recommendation task. I probably should not have revealed that. Now you'll judge my taste. A pure recommendation task is where we don't have any context, where we do not have search term. And then a different kind of recommendation task is video-to-video recommendation task. When you click Emily in Paris, what are the other titles that are similar to it? Now, the premise of this part of the talk is we can build one ML model to jointly serve both search and recommendation tasks. So first, let's double-click on what are the differences between a search task and a recommendation task. The first one being the context itself. For search, there is always a query that you type. So it's a user intent that is kind of provided to the system. Example is query in the input context for search, whereas for recommendation, it could be a video or it could be nothing, which is basically just profile ID or your user ID is the context. And then because they're usually part of different parts of the product, there are different engagements. So when you go to search, you you usually engage with a different part of the product. For example, in Amazon, when you search something, versus when you see Amazon homepage, it's recommendation. As a result, there are also different candidates that are retrieved for search and for recommendation, as well as there are people who work in industry know there's always like some business request based on which there are some last pass kind of business rules set up, so they are usually different as well. So the goal of this work was to develop a single contextual recommender system, which we name as Unicorn, Unified Contextual Ranker or Recommender System, that can serve all of search and recommendation tasks. And what's the benefit? Instead of having 4 different models, when you can have just one model, you need fewer scientists to develop it or fewer engineers to develop it. You can bring innovation to multiple places by just innovating on one model. So that's a huge benefit. And then these different tasks kind of benefits from each other. And as we can kind of, no one really loves taking care of tech debt, so lower maintenance cost as well as lower reduced tech debt. These are some huge benefit. And just a spoiler alert, we were successfully able to build this one model and replace 4 different models in Netflix production. And this is part of what powers Netflix search as well as some part of the recommendations today. So how do we go about doing it? Remember the differences in the context that I mentioned? We basically unified the context or unified the differences. First is unify the context. So instead of just having query and profile ID in the context, we add query, country, language, task type, whether it's a search or recommendation task. Then we also have a combination of data. We take user engagement data from across the products and mix them. So it's kind of a data-driven multitask learning. As well as we add context-specific features. So when it's a query, there are query-specific features. When it's just a source title ID, Emily in Paris, more like this. So we add those entity source title ID related features and so on. So here's an example of the task and its context. For search task, the context looks like something like this: query, country, language, and task equals to search. Whereas for title recommendation, it's source video, country, language, and task is title recommendation. So this is kind of data-driven model, parameter-driven multitask learning, which is allowing the model to learn unique behavior from these different tasks while also benefiting from each other tasks. And when we also combine all the engagement from all parts of the product, instead of training different models from different parts of the data, as well as the ultimate rank, whatever this model is ranking is still just likelihood of, let's say, play, that when a user comes in, whichever part of the product they come in, Netflix wants you to find something that you can play. Similarly, Amazon wants you to probably find something that is relevant to you. Here's an example of the model. So it's a fully connected deep neural network. I won't go into a lot of details of the architecture, but some certain things to highlight here in the model. We have entity features, which is basically the target, because we are ranking set of videos for Netflix. We are ranking set of listing for Amazon. So those are features about the final output, so target. Then we have context features like query, source title ID, like, for example, Emily in Paris or Stranger Things, and profile, like whatever we know from your behavior on the product, we also take those contexts into account. Other context features are like device type or time of the day. Maybe it's Saturday evening, you want to watch something else sitting with your friends or partner, versus it's Monday morning, you want to take a break during work, you're watching something else on Netflix. So it really depends on the context. And then context entity features as well. So for a given time target, what are some features? So those are called cross features. Those are very, very important. And then we have similarly all these categorical features for all these different categories. For real valued features, they are just basically numeric features. And then for any categorical features, we have embeddings in the model. And then it's a fully connected neural network with skip connections, so or residual connections. And they usually help with the model not forgetting some of the input context. And ultimately, the model tries to optimize for likelihood of positive engagement. In this case, in the context of Netflix, likelihood of positive engagement could be play. So this model then gets deployed in production, and this one model then powers search, powers title recommendation, powers pure personalization recommendation, and so on. And we are referring to this model as unicorn, because it's unicorn, serving 4 different canvases by one model. So how's this learning happening? What are some unique things about a model like that? Each of these different tasks are actually benefiting from each other. So each of these tasks, the rest of the task is called auxiliary task. So an example is when a user types stranger as a query and stranger thing as a source title ID. This model learns that the user really is looking for something similar. Through a query, the intent is, hey, show me Stranger Things. But when I click on Stranger Things as a title, the rest of the recommendation, I want to fetch a title that is similar to Stranger Things. Then also task type as context and feature specific to different tasks let the model learn trade-offs between the different tasks. When we train individual model for just one purpose, we are really kind of making this model be very narrow about its intent. Whereas when we are able to train one model for different tasks, it's able to learn from these different tasks, and it no longer remains as myopic. And in some way, I'm kind of trying to motivate the next part of the presentation that I'll show, which is foundation model, which is taking it even further down, where it's no longer, it's completely agnostic to any task. This is still specific to search and recommendation. The other additional aspects that I can share here is imputing missing context is very helpful. So for example, for some tasks, pure personalization tasks, or title recommendation tasks, you don't have query terms. But figuring out a way through a heuristic or some other model, imputing those query was very helpful. So for title recommendation, when we don't have query, some of the things I've done is like tokenize the source title name and treat it as a query, or somehow figure out, based on some heuristic, mapping an entity to a query, and so on. Also, something that ML practitioners know, that feature crossing can be very helpful in this case. There is a model architecture called Deep and Cross Network, DCNV2. That is what we are using here. That's very, very useful in case if you want to know more about it, come see me after the talk. With this unification, we were able to achieve either a lift or parity of performance for these different tasks. So in one go, we were able to replace 4 different machine learning models in production with this one model. So some system consideration here. Prior to this unicorn model being built, we had proliferation of ML models across the system. And this is in the context of Netflix. I have worked in other places, it's true. Like you train a model to solve a bespoke problem. So each of these system had to maintain all these different parts of the pipeline. So for example, for email notification, you needed a label preparation step, a featureization step, model training, and then you serve the model somewhere online, and then model hosting and inference has to happen. Each of these is also incurring its own cost. Similarly, for title recommendation or related items, the same steps have to be kind of repeated with different label, with different features, and so on. Similarly, for search, for category exploration, you name it. Both the offline part as well as the online part used to be done independently. Each of them requires some engineers and scientists to maintain it. And offline pipeline, online pipeline, there are failures, and so on. With Unicorn, we were able to replace those series of columns with this ML system, where we just now have difference in the label data generation preparation because it's still connected to the product. So for notification, we have a label preparation. For item, title similarity, we have a label preparation, and so on. For search, for category exploration, for pure personalization. So that's the only difference in the pipeline. And then everything becomes common. There is unified label preparation, unified feature generation, multitask model training. And then there is one way to kind of host the model, and then in different systems. And then as the user comes to the product, so a client makes a call to the service makes a call to the ranker, and then boom, we get the results. So it does definitely simplify both the offline pipeline as well as the online pipeline. However, for online infrastructure, there are some additional considerations. For example, different parts of the product, different online system has different SLA consideration. So for kind of mitigating that, what we do is we do specify or host the model separately for some products if there is a separate SLA. And we also have different knobs to optimize things like caching, whether in which canvas should we cache. For some canvases or for some part of the product, we cannot cache. Similarly, for some canvases, maybe latency is extremely sensitive, so throughput and SLA is very important. For some canvases, it's not. So we really kind of try to give those levers for online inference to kind of continue serving the product as it needs, whereas under the hood, the model has now fully been unified. So yeah, these are kind of some specific choices about inference that we made. Deploy the model in different system environment per use case. Provides knob to tune the characteristics of the model inference, including model latency, data freshness, caching, etc. And exposing a generic use case agnostic API for consuming systems. So what it enabled us is now any product partner can come in and say, OK, we have a search use case or a recommendation use case. They have an endpoint of model to take from, and they can go just run from it. And there are different knobs of whether to enable caching, what kind of context to provide this model. And it's much more self-serving in terms of the product partners to be able to use ML. And this really increases innovation velocity, as you can imagine. And to enable this flexibility, the API we have also enabled heterogeneous context input. So a pure personalization use case would just have user and country, maybe. A pure title recommendation might have user, or not even user, just source entity ID, and so on. And we also have enabled a way to have separate candidates set for each of these tasks. OK, so that was Unicorn, the model that unifies search and recommendation. Now let me kind of go over some specific aspects of foundation model, which is a user-specific foundation model that we built in Netflix. And then hopefully I can bring it together why I'm talking about two different models in the same presentation. So what is a foundation model or a user foundation model? Inspired by the effectiveness of large language model, example, GPT, Llama, within Netflix, we build a large model that can holistically learn member preference, both long-term and short-term, and be task agnostic. So the whole idea of these large models is the model's parameters are so big and the capability of the model is so large that we don't really need to kind of tell it about specific tasks. It can understand and learn a lot more tasks than a few specific tasks. So Unicorn was still specific because it was for search and recommendation. Here we build a large model to just generically understand what members are doing on Netflix. And that's applicable for other products too. So why even build a foundation model? Here are some few pointers. One is this is one model that can learn user long-term preference, short-term preference, as well as long-tail entity representation. It also reduces maintenance costs to allow operating with small teams. It makes it cost efficient because we just need to now train one model, and much fewer models, much more bespoke models can be deprecated. And innovation applied to one part of the product can immediately be applicable to other parts of the product. And now we are even going beyond the specific search and recommendation tasks that Unicorn was already able to replace. How do we go about building this foundation model? Imagine this user comes to Netflix. Maybe he or she has been, in this case, he has been on Netflix for 4 years. We know all their engagement that they have done. So first, let's say the user came to Netflix, discovered Stranger Things. It's a horror thriller show. Then the user binge watched this title, and then discovered another sci-fi title, and so on and so forth. This is the user engagement history, and it's an input sequence. So it's entire history of engagement about the user on the product. Side note, Netflix do not use any other demographic information about the user, only whatever they have engaged on the product. So there is a similarity we might have seen between LLM and this foundation model, between large language model and this foundation model in the context of Netflix. The similarity is the title or the entity that we have, so Stranger Things, Emily in Paris, that is equivalent to a word in the context of natural language. So we do one-hot representation with similar vocabulary size. It follows power law as in natural language and is sequential in nature because we are thinking about the user engagement on the product as a sequence, which is like a document of text. So instead of sentences, we have interaction trajectories. And the learning objective is also self-supervised fashion, same as large language model. Given history as context, predict the next word. In this case, predict the next video or next entity. And once we have this foundation model built, it will have fine-tuning capability like the other LLMs or video LLMs that we saw in the previous presentation. But what are the differences? One would argue that it's actually more difficult to really make this foundation model for a context like Netflix work compared to a large language model, because our understanding of user preferences and behavior is more restricted compared to our understanding of language, which has many centuries of understanding of language. So what are the specific differences? Words and titles are fundamentally different. Language has more structure. We understand more about semantics and syntax and grammar, whereas title and user behavior is very unique from one user's behavior to another user behavior. And both are power law distributed. Example is in the head, a word has things like stop word. We want to kind of remove those from the corpus that we are building. In case of titles, those stop words are popular titles. Titles that become extremely popular that it almost loses any information content because everybody is watching it. And at the tail, a word has more nuance, subtlety of a language. And when it comes to tail of the titles, it's those very niche, very unique tastes that just might be preferred for a few users and not most users. And we have similar problems as cold starting, popularity, and so on. So using the user history, then we kind of prepare this data, which is a big part, to train from pre-train. So this is, we are not using a GPT or a llama or something that has already been pre-trained, because this is trying to understand user engagement history and build a foundation model. So it's unique in its context. In the context of Netflix, there is one pre-trained foundation model. And we use a user history. Tokenization is important, similar to LLM. There is low signal to noise ratio. heterogeneity in the interaction. There are engagements like, oh, you play a title, or you thumbs up a title, or you add to my list ad. Depending on the domain, in the context of e-commerce, you add to cart and then purchase and see email notifications and so on. Important consideration is also how do we represent an interaction. One interaction can be simultaneously on a show, on a row, on a genre type. And interaction context like time, duration, language, devices, all these are important things that we want to inject into this foundation model in order for it to be truly deeply able to understand the product and the user preferences. So here's an example of how we go about tokenizing this user interaction history. So for example, this user came in, played Stranger Things, then added to my list Wednesday, then played the Gray Man, thumbs up Gray Man, again went back and played Stranger Things, and then moved on to Squid Game. In order to tokenize, if we just use raw history, is going to be, the context length is going to be enormous. So typically, we do some kind of roll-up. And similarly, in language, we also do some kind of tokenization mechanisms to better represent the data while not blowing up the vocabulary size. Here, we do roll-up, where we consider within a given window of time, if you have watched the same title, it has kind of similar information content, so we roll it up. As you see, there is one Stranger Things, but from the series of 3 Stranger Things later is just we take one Stranger Thing, similarly for Squid Game. And then this becomes the input to the foundation model that we are training now. So what do? We ultimately train a transformer model, a few stack transformer. This is our member foundation model, and it's very similar to the architecture of GPT-4, except it is not trained on language, it's trained on user preference history, which has all the characteristics of a natural language, but it's on a product engaged, a user product engagement. And this is the transformer that is trained on user history, specifically is a decoder-only model. That's why it's similar to GPT-3, GPT-4, with multiple objectives. The objectives being what will be the next title that the user will engage with. The second objective is what are the intent? Do the user wants to watch a movie or a game? Or do they want to watch horror versus comedy, so genre, and so on. And the reason we want to train this multi-objective model is to make sure that we have enough information that it's able to generalize the user understanding instead of learning about one specific thing, which is recommendation. A little bit more details about the model itself, if you're interested. It's a hierarchical multitask learning model, wherein previously, as I showed, the user input sequence goes in, then we create the input vector, and then we have a 4-stack transformer, where the first stack is understanding user intent, like whether you want to watch a movie versus a game, play games, whether you're interested in horror shows versus comedy shows, and so on. And then the next one is a recommendation task, which is the next item prediction task. OK, this is kind of the foundation model. We were able to train it, and this model is able to understand user preference very, very well, so that individual bespoke model is not, they do not need to reinvent the wheel. And is much, much cheaper to train one foundation model than each of these individual bespoke model, relearning these user patterns again and again. So in all this, you might be wondering, OK, where is the Harry Potter and what is the magic here? We just talked about ML. I would argue, OK, this might be a very lame opening slide, but I'm going to try it. I would argue that the transformer is the Harry Potter, and the transformer as in the foundation model is the Harry Potter, and the personalization that it brings is the magic. Because, do you remember the unicorn model that I described? At nowhere, unicorn was personalized. But what we did is after we trained this foundation model, or the Harry Potter, I was able to bring that foundation model into unicorn, and within one go, one click, or one effort, we were able to personalize 4 different canvases directly by just leveraging the user foundation model. It brought a huge lift offline, both for search and recommendation tasks, 7% and 10% increase, as well as it was a pretty big lift online as well. I'm not allowed to talk about online metrics. But as you see, like, we saved a lot of effort, because otherwise, the alternative is for each of these different canvases, we would have had to think about how we personalize it, how we learn the trade-off between context and relevance and personalization. But because this foundation model is so powerful and is capable of understanding the nuances of user preferences, by just combining it or bringing that information into Unicorn model, we were immediately able to personalize search, personalize a pre-query, which is a purely personalized canvas. We were able to personalize title recommendation, and so on. So that's where the magic happened. Here's an example. The previous 2 row is recommendation, is the result from query S. This is on one of the test profile. This test profile do not watch kids title. And as you see, before we had foundation model injected, the first 2 rows is from pure Unicorn results. There are some kids title. Even though most of the recommendation results are relevant, like Suits, Spy Game, and so on, Seinfeld, there are some kids title. After we put in the foundation model into Unicorn, those kids title were gone, and all the results became much more relevant. This is just an example, just kind of motivating that we were able to not only bring in personalization with foundation model, but because the foundation model understands the user preference and nuances, we were able to do a good trade-off between personalization and relevance. So what we covered so far, we developed a unified contextual recommender model, Unicorn, to power Netflix search and recommendations. Sorry, recommendation is missing here. Then we developed a large transformer-based foundation model to holistically learn member preferences grounded in the Netflix content understanding. And then we leveraged the magic of FM, a foundation model in Unicorn, to personalize all the search and recommendation tasks powered by it. It all looks great, but there were challenges. So I guess the first big promise then, before going to the challenges, is to truly leverage this magical power of foundation model. We went even beyond Unicorn, and we were able to leverage this foundation model into other models that required personalization. And we were able to successfully start within very, very short ramp-up time, personalize any canvas, because this foundation model learns a personalization very well. Okay, so what were some of the challenges? Of course, the large foundation model to be trained, we need a lot of training optimization, so efficient algorithm for training. And there is a huge literature on optimizing a large foundation model now, including fast attention and how we quantize the model and so on. I'm just highlighting some of the challenges that we had to address without going into details. Then substantial computing resource needed to be assured, and including like thinking about how to best utilize the GPUs that we had, how to shard the data, how to optimize GPU training, and so on. And then after the model was trained, this is a large model. How do we think about serving? How do we serve? Do we cache? Do we not cache? Do we do some batch compute? How do we keep the latency of the downstream application like Unicorn that is consuming foundation model while not increasing the cost really, not blowing up the cost? And cost of prioritization was a big one, where we had to go with multi-GPU, both for training as well as inference, and while figuring out how to optimize for cost, and also robust evaluation, both offline and online. For these challenges, I am not able to share all the details, but these are, I think, will be common among every company, every team that is trying to think about serving large models in really high production traffic. What are the other challenges? Personalization is good, but not in all cases. Over-personalization is not good. In the context of search, if you type Paris and you see a highly personalized result, but none of the titles has PARI in it, or there is no lexical relevance, then it's not going to be good results. So how do we trade off personalization and relevance? Instead of over-personalizing, how do we make sure we have the right balance? That's a very important consideration. And then it goes back to the general problems of recommendation systems in general, like concentration effect, filter bubble. How do we think about it? The rewards and objectives are very important here. What are the online metrics? How do we evaluate whether the model that we build is good or not? Core metric, secondary metric. And then going back to the offline training world, where how do we think about negative sampling, rewards, and so on. So I just wanted to highlight some of the different dimensions that we had to consider for making this whole system of Unicorn and foundation model work. With that, here's my key takeaway. It is possible to build a large foundation model that can holistically capture member preferences, both long-term and short-term. A single unified model, Unicorn, aware of diverse contexts can perform and improve both search and recommendation tasks. While the magic of personalization can be easily brought within Unicorn via this foundation model and even beyond Unicorn, while optimally trading off relevance and personalization. But more importantly, several infrastructural and modeling considerations need to come together for systems like Unicorn and foundation model to work at the scale of 300 million plus users, as highlighted in some of the work and some of the challenges that I mentioned. With that, we have some papers for both the Unicorn model as well as foundation model. Here are some links, and this is my LinkedIn if you want to stay in touch. That'll be all. Thank you.
Thank you for great presentations. So before we go into the Q&A, please, if you haven't already, download the mobile app and share your feedback for the presentation. We have about 10 minutes for the Q&A, and we should have folks where the volunteers, they walk out, but they never walk in. So we'll need some help. But since I have the mic, I'm going to ask the first question.
There are a few hands also at the back, but
yeah,
go for it.
The volunteers are not here. They went out. The Netflix there are members across the globe. The foundation model that you guys have, is it for all members?
Yes.
Wow, okay, that's a lot of members. All right, so let's start here, and then I'll try to run the mic.
Thank you very much for the talk, very interesting. I have a simple question. I think in the world of large language models, it is a normal technique to make fine-tuning of the fundamental model for concrete tasks. Why do you use it, or why, or if not, why you don't use it for fine-tuning for recommendation, fine-tuning for searching, fine-tuning for maybe something similar task?
Yeah. Thank you for your question. The question was, in the world of LLMs, it's very common to leverage the large language model to fine-tune for search and recommendation or any application. Whether we use it, whether we also fine-tune the foundation model for search and recommendation. If not, why not? Yeah, so I didn't go into details about that integration of foundation model into Unicorn, right? Like I basically said, oh, we have a foundation model, we merge it with unified contextual ranker, and then boom, recommendation is personalized. The fine-tuning kind of comes in play there. How we leverage the foundation model into an application model, like so Unicorn in this case. There are approaches where we fine-tune it take the TF graph or the PyTorch graph and combine it with the application model and fine-tuning jointly as a part of the training. There are also approaches where, depending on the use case, we fine-tune it on a specific data, the foundation model, and then just takes the embedding or something. So there are different, I didn't really go into the technical details of how we combine it, but yes, very relevant question, and fine-tuning is definitely one of the most leveraged approach.
All right, question in the back.
Oh, yeah, that works, cool. Great talk, thanks. One key difference as well between text and titles is that text, I guess, is more static, right? There's a dictionary, and we only add so few words a year. But you're releasing so many titles a day. How often are you having to retrain this model? Because obviously, it feels like sometimes TV shows blow up overnight, and everyone you know's watched it. So are you forcing recommendations on people, or? Yeah.
Thank you for your question. Yeah, the question is that there is a fundamental difference between text and titles, where titles are dropped and released every day, every week, whereas text is a static vocabulary. How do we handle cold starting? And how often do we train the foundation model in order to handle those fresh titles? And this actually goes back to the first question that was asked, where we don't retrain or pre-train the foundation model on a daily basis, but we do fine-tune it for any new titles. So as you can imagine, there are checkpoints of the model saved, and then with any new incremental title, the weights can be updated to account for that fresh title.
Other questions?
Thank you. I wanted to ask, how do you account for things like diversity as well as sort of making sure recommendations are editorially appropriate. And I also wanted to ask about your culture to running experiments and A/B tests and how often you might do those.
Thank you for your question. So the question is about how do Netflix or this work accounted for diversity, and there was a second part?
Yeah, sort of, editorial appropriateness of recommendations.
Editorial appropriateness of recommendation, and the third was about culture. I'm representing myself here, so I will skip the question on culture, not take that, but the first two about diversity and editorial appropriateness. Diversity really comes from the data, so there are different ways to build the data that we train the foundation model on. If you train it only on a certain part of the product, then you can kind of have basically closed loop data, then it can just like be over-optimizing on whatever was shown to the user first. What we do is open up and train it on anywhere on the product, whatever user has engaged across the product. There are other approaches that we leverage without being able to commit which of these is in production. We also have explore exploit, where you have explore, where you don't show the results from the model, but you have with some likelihood to explore. And that helps in diversifying the data. But then in objective also, there are ways you can build the reward function in objective to ensure diversity. One common model objective is DPO, which is basically to introduce diversity in the machine learning model itself. Editorial, we have a pretty big setup for editorial reviews. And anything that shows to Netflix member directly has some checks and balances, but it's still, it's a combination of ML-driven and checks and balances from our content creators, from editorial partners. But it's just impossible at the scale to have every result show up editorially. But we do take that very seriously, experts' opinion about what ends up being shown to the member.
Okay, other questions?
Thank you for the presentation. My question is, after you have trained and built your foundation model, were there any emergent behaviors that you have explored or found out that were not intended after the training?
The question was, after the foundation model was trained, if there was any emergent behavior that was found out that was not expected during the training. Nothing that comes to mind. It is, even though it's Netflix foundation model, the scale is still pretty small compared to LLMs and stuff, because we don't need the capability that we're trying to learn is on just specifically for Netflix members. And I can't comment on it because I don't think we found anything. And there is a blog that details all the details of foundation model that we have built, but there is no mention of the emergent behavior, nothing that I can comment on. Yeah.
Thank you.
Thank you.
All right, we have time for one more question.
Hi, yeah, thanks for the talk. I actually had two questions, but I'm going to boil it down to one. Do you also use the recommendation engine internally now? Because from what I understand, Netflix is a big content producer as well, and you need to make a lot of decisions what content you want to produce.
This is for member recommender system. So it's everything that is facing the customers. When you come to netflix.com, either on mobile or app. On the content side, I don't work on the content side, so I can't comment on the content side at all.
Thanks.
All right, maybe one more?
You've got 5 more minutes.
Yeah. Any question? Raise your hands if you have one question. Up here, front.
You just mentioned web, mobile. So is the model platform agnostic? And if so, how do you manage to basically provide the same suggestions for the same queries that the users can access from different platforms? So you have Xbox applications, web, mobile.
Yeah, that's a great question. The question is, is the model platform agnostic? Or maybe I shouldn't have tried to do that. The context that I mentioned in the model, talking about Unicorn, this context feature does have the device type. So it is learning the different behavior from different platform, if there is any. But we don't train a different model. That's the whole point. We don't train a different model for different platform. It's all learned within the model based on the user preferences, historical engagement.
All right, one more over here.
Thank you very much for the talk. I had the question. So since Netflix has a lot of content, which is primarily visual content, do you extract any attributes like video vectorization or video-based tagging or anything not related to the metadata? I mean, not related to the names of the titles, but instead the contents themselves.
Thank you for your question. Yeah, the question is, because Netflix has a lot of video and image data, do we leverage other modalities beyond text and user engagement history in the foundation model? The answer is we try all sorts of things. This part I won't be able to disclose about the specific features that are being leveraged, but we do go beyond textual modality as well. And as you would imagine, not everything that we try gives benefit. So we try experiment offline and see what is lifting the offline metrics. So we do leverage other modalities beyond just user history. Thank you.